Scapa Flow, Scotland, June 12, 1974. Dr. James McIntyre stands on the deck of the salvage vessel Resolute, watching as cables strain against 55 years of North Atlantic water pressure. Below, in the dark water of Scapa Flow, rests the wreck of SMS Derfflinger, a German battlecruiser that has lain here since June 21, 1919, the day the German high seas fleet scuttled itself rather than surrender to the British. McIntyre is 46 years old, a marine archaeologist from the University of Edinburgh, who has spent 2 decades studying the sunken fleet. But this recovery is different. The Royal Navy has finally authorized full salvage of Derfflinger's engine room section, where preliminary sonar surveys detected something unusual, machinery that doesn't match any known specifications, modifications that weren't in original construction documents, evidence of desperate improvisation in the fleet's final months. The first section breaks the surface, water streaming from rusted steel that once represented the pinnacle of German naval engineering. McIntyre's team swarms over it immediately, cameras documenting, specialists examining, everyone aware they're about to open a time capsule from the death throes of Imperial Germany. What they will discover over the next 18 months isn't just maritime archaeology. It's an autopsy of an empire, written in corroded metal and failed welds, telling the story of how the second most powerful navy in the world destroyed itself not through defeat, but through the invisible collapse of industrial infrastructure that made it possible. The strategic context of Scapa Flow was legendary in British naval history. This natural harbor in the Orkney Islands had been the Royal Navy's primary anchorage during World War I, the base from which the Grand Fleet controlled access to the North Sea and blockaded Germany. After the armistice in November 1918, 74 ships of the defeated German high seas fleet were interned here, while Allies negotiated the Treaty of Versailles. On June 21, 1919, under orders from Admiral Ludwig von Reuter, the German crews had opened seacocks and scuttled their ships, rather than allow them to be distributed among Allied powers. 52 ships sank in a matter of hours, the greatest act of maritime mass suicide in history. Over the following decades, most of the wrecks were salvaged for scrap metal, but the deepest wrecks, including 3 battlecruisers, remained on the seafloor, gradually becoming part of Scapa Flow's ecosystem and legend. They were diving attractions, war graves, and increasingly, archaeological sites of historical significance. McIntyre had been studying the Scapa Flow wreck since 1954, when as a young naval officer he had participated in diving surveys. He had become fascinated not just with the drama of the scuttling, but with what the wrecks could reveal about German naval capabilities, strategies, and ultimately the reasons for their defeat. The German high seas fleet had been, on paper, one of the most formidable naval forces ever assembled. Modern dreadnoughts and battlecruisers, excellent crews, sophisticated tactics. Yet it had been effectively neutralized by the British blockade, venturing out only once for a major engagement, the Battle of Jutland in 1916, which was tactical German victory but strategic British success because the German fleet retreated and never again seriously challenged British naval supremacy. The standard historical narrative blamed German naval impotence on strategic caution, on Kaiser Wilhelm II's reluctance to risk his precious fleet, on Admiral Reinhard Scheer's conservatism after Jutland's casualties. But McIntyre suspected there was more to the story, something hidden in the physical evidence of the ships themselves. His hypothesis, controversial among colleagues, was that the German fleet's inactivity in the final 2 years of the war wasn't primarily strategic choice, but operational necessity, that the ships had become increasingly unseaworthy due to material shortages and maintenance failures caused by the British blockade. The Derfflinger salvage would provide the evidence to test this theory. The first week of salvage operations yielded immediate anomalies. The turbine housings, when sections were raised and opened, showed repairs that weren't documented in any German naval records, welds using different metal compositions than original construction, bearings replaced with units that appeared to be of different specifications than designed, pipe fittings that didn't match standard German naval engineering. Dr. Sarah Henderson, McIntyre's metallurgist colleague from Imperial College London, examined the first samples in the shipboard laboratory. Her initial findings were puzzling. "James, these repair welds are wrong. The metal composition doesn't match the structural steel. It's lower grade, higher carbon content, inconsistent grain structure. This would create differential stress under operational loads." "Wrong as in poorly done?" McIntyre asked. Wrong as in using whatever materials were available rather than specified materials. Look at these bearings. They're brass, but the composition is off. Too much zinc, not enough copper. They would have worn out much faster than proper naval bearings. Over the following days, as more sections were raised, a pattern emerged. Derfflinger had undergone extensive repairs and modifications between 1917 and 1919, but those repairs showed increasing desperation in material quality and engineering standards. The propeller shaft bearings were particularly revealing. McIntyre examined them personally, running his hands over surfaces that showed wear patterns inconsistent with normal operation. These were failing, he said to his team. Look at the scoring, the uneven wear. These bearings were operating far outside their design tolerances. Lieutenant Commander Robert Thompson, Royal Navy liaison to the project and himself a marine engineer, studied the turbine blades that had been carefully extracted. Dr. McIntyre, these blades show cavitation damage that suggests they were running in steam conditions that were too hot, too variable, or contaminated. See these pitting marks? That's erosion from impurities in the steam. Proper naval boiler water treatment would prevent this. So the boilers weren't maintaining proper water quality? McIntyre asked. Correct. Which means either the water treatment chemicals weren't available, or the crews didn't have proper training, or both. Either way, this ship's propulsion system was degrading rapidly from internal corrosion and contamination. McIntyre stood back, looking at the array of components spread across the salvage vessel's deck. Corroded piping, damaged bearings, eroded turbine blades, improvised welds. Each piece was a word in a sentence that was beginning to form. Derfflinger hadn't been scuttled at peak operational condition. It had been scuttled as a ship already dying from within. The boiler sections came up next, and with them, the story became clearer and more disturbing. The boilers showed extensive repair work, with patches welded over areas where the original steel had corroded through. But more significantly, the chemical analysis of deposits inside the boiler tubes revealed a shocking finding. Dr. Henderson ran the spectroscopy 3 times to confirm. James, the water in these boilers in their final months was essentially untreated seawater. There are salt deposits, calcium buildup, evidence of severe scaling. This would have reduced thermal efficiency dramatically and accelerated corrosion at catastrophic rates. Why would they run salt water through boilers designed for treated freshwater? McIntyre asked, though he was beginning to guess the answer. Because they didn't have access to proper boiler treatment chemicals. Chromates, phosphates, alkaline compounds, all of these were in short supply in Germany by 1917 due to the blockade. They were needed for other industries, other weapon systems. The Navy had to make do with increasingly inadequate water treatment. Lieutenant Commander Thompson shook his head in professional horror. Running a high-pressure naval boiler on inadequately treated water is asking for catastrophic failure. These ships were time bombs waiting to blow their boilers under combat stress. The implications were staggering. The German high seas fleet hadn't been held in port primarily by strategic conservatism, but by operational reality. The ships were becoming mechanically unreliable due to material shortages caused by the British blockade. Each month that passed, each repair made with substandard materials, each compromise in maintenance procedures moved the fleet further from combat readiness. McIntyre requested access to British naval intelligence files from 1917 to 1918, documents that had been classified for decades but were now being released. What he found confirmed the physical evidence. British intelligence had intercepted German naval communications discussing chronic machinery problems, delayed maintenance, shortage of spare parts, difficulty maintaining steam pressure. One intercepted message from October 1918 from an engineering officer aboard SMS König read, "Starboard turbine bearings require replacement, but spares not available. Running reduced power on that shaft. Port boiler number 3 showing pressure irregularities due to scale buildup. Water treatment chemicals exhausted. Request priority resupply." The response, also intercepted, "No spares available, no chemicals available. Maintain operations as possible. Minimize high-speed operations." It was a death sentence written in bureaucratic language. Maintain operations as possible, but we cannot provide what you need to actually maintain operations. Keep going until you break down completely. As the salvage operation continued through summer 1974, McIntyre's team expanded their investigation beyond just Derfflinger. They conducted non-invasive sonar surveys of the other sunken battlecruisers. Seydlitz and von der Tann, and analyzed archival photographs taken of the interned fleet before the scuttling. The photographs were revelatory. When examined closely with magnification and modern enhancement techniques, they showed details that contemporary British observers hadn't noted or hadn't understood the significance of. External hull patches indicating internal structural repairs, rust streaking that suggested corrosion beyond normal weathering, ships riding slightly off their designed waterlines. Dr. Michael Chen, a naval architect from Glasgow University who joined the project, analyzed the photographs with professional expertise. These ships look operational from a distance, but up close you can see they're deteriorating. This rust pattern here, that's indicating that internal structural members have corroded through and been temporarily patched. This waterline discrepancy suggests internal flooding in ballast tanks that's been compensated by pumping but not repaired. These aren't just cosmetic issues. These are signs of systematic structural failure. The team also discovered something in Admiralty archives that had been overlooked by historians. Reports from British sailors assigned to monitor the interned German fleet in early 1919. One report from a young lieutenant conducting an inspection tour noted, visited engineering spaces of several German vessels, noted extensive evidence of recent repairs, many appearing makeshift. German engineer officers appeared embarrassed by condition of machinery. One officer, speaking English, admitted that the fleet had been barely operational for final year of war due to shortage of proper materials for maintenance. McIntyre read that report aloud to his team with growing excitement. This confirms everything we're seeing in the physical evidence. The German fleet wasn't inactive because their admirals were cowards, or because the Kaiser was sentimental about his ships. It was inactive because the ships were mechanically degraded to the point where combat operations would have risked catastrophic machinery failures. Henderson added another dimension. And if the British knew this, or suspected it, then the blockade was even more successful than previously understood. It wasn't just starving German civilians. It was systematically dismantling German industrial capability, including the ability to maintain their most sophisticated weapons systems. The British blockade had been warfare not by destroying the enemy, but by preventing them from maintaining what they already had. It was victory through industrial strangulation. Autumn 1974. The investigation deepens into German industrial records. McIntyre traveled to Germany, to the Bundesarchiv in Koblenz and the Naval Archives in Wilhelmshaven, seeking documents that would provide German perspective on what the British salvage was revealing. He was accompanied by Dr. Klaus Richter, a German naval historian who had studied the high seas fleet extensively and was intrigued by McIntyre's findings. Together they found documentation that painted a damning picture. By 1917, the German Navy was competing with the Army, the U-boat force, and civilian industry for increasingly scarce strategic materials. Copper for electrical systems and bearings, nickel for high-strength steel, various chemicals for everything from explosives to water treatment. A memo from the Reichsmarinamt, Imperial Naval Office, dated March 1918 laid out the crisis. Surface fleet maintenance requirements for current quarter, 2,400 tons copper for condenser tubes and bearings, 180 tons nickel for turbine blade alloys, 340 tons zinc for brass fittings, 15,000 tons petroleum for boiler fuel. Available allocations, 600 tons copper, 25% of requirement, 40 tons nickel, 22% of requirement, 200 tons zinc, 59% of requirement, 11,000 tons petroleum, 73% of requirement. Deficit must be addressed through alternative materials, reduced operations, or deferred maintenance. Richter translated the implications. They're being told to operate a modern battle fleet on a quarter of the copper they need, a fifth of the nickel, and 3/4 of the fuel. This is impossible. You cannot maintain high-pressure steam turbines under these conditions. Further documents showed the cascading consequences. Engineering officers requesting materials that couldn't be supplied, maintenance schedules being extended beyond safe limits, operational orders restricting high-speed operations to preserve machinery, increasingly desperate requests for any materials that could substitute for specified components. One poignant document was a letter from the chief engineer of SMS König to his family, found in personal archives. "We do our best with what we have, but the ships are dying beneath our feet. We patch and we improvise, but every month the machinery grows less reliable. If we had to fight the British now at full speed and full power, half the fleet would break down before we reached the battle area. The officers know this. The men know this. Perhaps even the British know this. We maintain the appearance of a fleet in being, but it is theater. We are stage props, not warships. McIntyre read that letter in the Bundesarchiv reading room and felt the weight of historical tragedy. Winter, 1975. Salvage operations resume after weather delays. When work resumed in spring 1975, the team focused on Derfflinger's electrical systems and fire control mechanisms, the sophisticated technology that made early 20th century battleships effective. What they found was even more disturbing than the propulsion problems. The electrical cabling, when sections were recovered and analyzed, showed insulation that had deteriorated far beyond what should occur in ships only 5 years old when scuttled. The rubber insulation was brittle, cracked, in many places completely failed. Salt water had penetrated into cable runs, corroding the copper conductors. "This is wrong," said Dr. Patricia Walsh, the team's electrical systems specialist. "This level of insulation failure should take decades, not 5 years. Unless..." She ran chemical analysis on the insulation material. Oh no. This isn't standard electrical insulation rubber. This is lower grade material, probably substituted due to shortage of proper rubber compounds. Natural rubber comes from tropical colonies, which Germany lost access to during the blockade. They were substituting inferior synthetic or reclaimed rubber that degraded rapidly in marine environment. The fire control systems, the optical rangefinders, the mechanical computers that calculated firing solutions, the electrical transmission systems that connected them, were in even worse condition. The optical systems showed lens degradation that suggested improper glass composition. The mechanical computers had gears made of brass with wrong alloy composition, showing excessive wear. Lieutenant Commander Thompson examined the fire control equipment with growing professional dismay. These are supposed to be the finest naval gunnery systems in the world. The Germans were famous for their fire control, but these components are degraded to the point where accuracy would have been seriously compromised. The rangefinders have lens aberrations. The transmission gears have excessive backlash from wear. The electrical firing circuits have insulation failures. If Derfflinger had fought in 1918, her gunfire accuracy would have been dramatically reduced from her 1916 capabilities. McIntyre was assembling a picture of systematic degradation across every system of the ship: propulsion, electrical, fire control, structural integrity. Each system had been compromised by material shortages that forced use of inferior substitutes, which then failed prematurely, which then required more repairs with more inferior materials, in a death spiral of declining capability. "This is why they didn't fight," McIntyre said to his team. "Not because they were afraid, but because they knew their ships were no longer capable of sustained combat." The Battle of Jutland in 1916 was probably the last time the high seas fleet was actually combat-ready at designed capability. Spring, 1975. The team discovers evidence of attempted concealment. One of the most disturbing discoveries came from documents found in sealed compartments aboard Derfflinger, papers that had survived in waterproof safes and provided direct testimony from the crew's final days. These included engineering logs from 1918-1919, that documented the progressive mechanical failures in stark technical language. Port turbine bearings replaced with unauthorized substitutes due to material shortage. Vibration increased 40% above tolerance. Maximum speed reduced to 22 knots, designed maximum 27 knots. Starboard boiler number 2 removed from service due to tube failures. Boiler number 4 operating at reduced pressure due to scaling. Overall propulsion capability estimated at 65% of design. But more revealing were handwritten notes from engineering officers discussing the need to conceal the true state of the ships from German High Command. One note read, "We have been ordered to report all ships as operational for inspection. This is technically true only if operational means floating. We are to show the Admiral Stab only systems that appear functional, and explain that other systems are temporarily offline for routine maintenance. The truth, that we lack materials for proper repairs, is not to be mentioned." It was evidence of institutional denial. German Naval High Command wanted to believe the fleet was operational, so subordinate officers told them what they wanted to hear, creating a gap between reported capability and actual capability that grew wider each month. Dr. Richter, the German historian, was visibly disturbed reading these documents. This explains something that has always puzzled historians: why German naval planning in 1918 still assumed the high seas fleet could conduct major operations when it never attempted them. The planners didn't know the true condition of the ships because the engineers were pressured to report them as operational. McIntyre found a memo that summarized the tragedy with bureaucratic clarity, dated April 1918, from Admiral Scheer to the Admiral Stab, marked Secret. Fleet operational capability has declined due to prolonged inactivity and maintenance challenges. Estimate 60–70% of major units could conduct combat operations, though not at designed maximum performance. Recommend against major fleet action until material situation improves. The response from higher command: fleet must remain reported as fully operational for strategic deterrence value. Enemy must not know of any capability reduction. It was the institutionalization of self-deception. Maintain the appearance of strength, even as the actual strength dissolves, because admitting weakness would be strategic defeat. But the result was that Germany continued planning as if it had a functioning battle fleet, when it actually had an expensive, prestigious, operationally limited liability. Summer 1975. Comparative analysis with British vessels. To establish proper context, McIntyre's team conducted comparative analysis with British warships of the same era. The Royal Navy provided access to HMS Iron Duke, a battleship that had served throughout the war and was preserved as a depot ship. The contrast was illuminating. Iron Duke's machinery, though also showing wear from wartime service, displayed none of the desperate improvisation visible in Derfflinger. Repairs had been done with proper materials. Maintenance had been conducted on schedule. Systems showed normal operational wear, but not the premature failure and substandard replacement that characterized the German ship. The difference, explained Commander Thompson, is access to global resources. Britain had the entire empire to draw on: rubber from Malaya, copper from Canada, nickel from Australia, petroleum from Persia. When British ships needed replacement parts, proper materials were available. The Germans had only what they could produce domestically or import from neutral countries, and that was never enough. Dr. Chen conducted stress analysis on comparable components from both ships. The British turbine blade shows wear consistent with designed operational life. They were running at full capability for the entire war. The German turbine blade shows material fatigue and cavitation damage, suggesting it was operating beyond design limits, probably because inferior alloy composition couldn't withstand the stress of high-performance operation. The analysis extended to crew living conditions aboard the ships. British vessels maintained reasonable habitability throughout the war. German vessels showed increasing deterioration, ventilation systems failing, sanitation systems compromised, living spaces becoming progressively less habitable. A British intelligence report from December 1918, interviewing German sailors after the armistice, noted, German naval personnel report poor living conditions aboard ships during final year of war. Food quality declined, heating systems often inoperative, medical facilities inadequate, morale described as very poor, with increasing disciplinary problems. McIntyre connected this to the mechanical failures. It's all part of the same syndrome. The material shortages didn't just affect propulsion and weapon systems, they affected everything: habitability, nutrition, morale. By 1918, the German high seas fleet wasn't just mechanically degraded, it was socially degraded. The crews knew the ships were falling apart, knew they couldn't really fight effectively, knew they were just sitting in port, waiting for a war to end. That's why the mutinies started in October 1918. Not because the sailors were cowards, but because they understood the futility. The British blockade had achieved victory not through dramatic naval battles, but through patient strangulation of the industrial system that made modern naval warfare possible. Autumn 1975. Historical reassessment begins. As McIntyre's findings became known in academic circles, they sparked a fundamental reassessment of World War I naval history. The standard narrative, that German naval caution after Jutland was strategic choice, was being replaced by a more complex understanding that it was strategic choice forced by operational reality. A symposium at the Royal Naval College in Greenwich brought together naval historians to discuss the implications. McIntyre presented his findings to an audience that included veterans of World War II, serving officers, and academics. The German High Seas Fleet, McIntyre explained, represents one of history's most expensive deterrents that ceased to deter because the enemy eventually realized it couldn't actually function. By late 1917, British naval intelligence strongly suspected the German fleet's material problems. By 1918, they were fairly confident that a major German sortie was unlikely, not because of German caution, but because of German capability limitations. Dr. Arthur Marder, the preeminent British naval historian, asked, "Are you suggesting that Britain won the naval war not through superior strategy or tactics, but through superior logistics and industrial capacity?" "Yes," McIntyre replied. "The Battle of Jutland was tactically inconclusive, but strategically decisive because it demonstrated that the German fleet could fight effectively once, but sustained operations at high tempo would have revealed the material limitations. The Germans understood this, so they returned to port and essentially never came out again. Britain won by making it impossible for Germany to maintain a competitive fleet through blockade of strategic materials. The implications extended beyond naval history into broader understanding of industrial warfare. World War I had been decided not primarily by tactical brilliance or strategic genius, but by industrial capacity and access to global resources. Germany, for all its military excellence and technological sophistication, couldn't overcome the fundamental disadvantage of being a continental power blockaded from global trade. A Royal Navy admiral in the audience commented, "This suggests that modern naval warfare is less about ship design and crew quality than about the industrial and logistical systems that sustain the fleet. A technically superior fleet that cannot be maintained is inferior to a technically adequate fleet backed by robust supply chains." "Precisely," McIntyre agreed. "The German ships were probably better designed than British ships ton for ton. But better design became irrelevant when the Germans couldn't maintain their designs to operational standard, while the British could maintain theirs. Quality without sustainability loses to sustainability without peak quality." It was a lesson that would influence naval strategy for decades. The fleet you can maintain is more important than the fleet you can build. Winter 1976. Final salvage operations and comprehensive report. The last major section recovered from Derfflinger was the Admiral's cabin area, which contained more documentation, operational orders, personal diaries, correspondence that provided human context to the mechanical evidence. Admiral von Reuter's own diary, preserved in a waterproof case, provided the most poignant testimony. His entry from May 15, 1919, 6 weeks before the scuttling, read, "We maintain discipline and routine, but we are custodians of corpses. These ships will never fight again, and even if released to us, they could not fight. They have been too long without proper maintenance, too long without adequate materials for repair. The high seas fleet is dead. It died somewhere in the final year of the war, not from British shells but from British blockade. We scuttled corpses today, not warships. Perhaps that makes the act less tragic, or perhaps more tragic. I cannot decide." McIntyre read this to his team as they completed their documentation. The salvage operation had recovered hundreds of artifacts, thousands of photographs, extensive material samples, and most importantly, historical understanding that changed how naval historians would view the war. The final report, published in 1976 as a comprehensive technical monograph, concluded, "The German High Seas Fleet, which in 1916 represented one of the world's most formidable naval forces, was rendered operationally ineffective by 1918, not through defeat in battle but through systematic degradation of material capability, caused by blockade-induced shortages of strategic materials. The ships remained afloat and maintained appearance of operational capability, but their actual combat capacity had been severely compromised by the use of substandard repair materials, inadequate maintenance due to shortage of proper supplies, and declining crew morale resulting from recognition of these problems. This represents a form of strategic victory achieved through industrial attrition rather than tactical engagement. The British blockade did not directly destroy the German fleet, but made it impossible for Germany to sustain the fleet at operational readiness. The result was self-imposed inactivity, followed by self-destruction. The implications for modern naval strategy are profound. Technological superiority and tactical excellence are necessary, but insufficient. Sustained naval capability requires robust industrial supply chains, access to strategic materials, and the logistical infrastructure to maintain complex systems under operational stress. Victory in modern naval warfare belongs to the power that can sustain its fleet, not merely the power that can build the most impressive ships. 1977, 1980. The broader impact of the findings. The Derfflinger salvage findings influenced military thinking far beyond naval historians. During the Cold War, when NATO and Warsaw Pact forces faced each other with sophisticated weapon systems, the lesson was clear. High-technology weapons are only as effective as the industrial infrastructure that maintains them. The U.S. Navy incorporated McIntyre's findings into logistics planning, emphasizing supply chain resilience and material redundancy. The concept of sustainable readiness, the ability to maintain operational capability over time under stress, became central to force planning. Soviet military analysts studied the case intensively. They recognized uncomfortable parallels. The USSR, like Imperial Germany, was a continental power with limited access to global resources, maintaining a sophisticated military through centralized production, but potentially vulnerable to blockade or supply disruption. In academic circles, the Derflinger analysis contributed to broader understanding of how wars are actually won and lost. The traditional focus on battles, commanders, and tactical decisions was supplemented by recognition of the critical role played by industrial logistics, resource access, and maintenance infrastructure. Dr. McIntyre continued his research, expanding it to other aspects of German military capability. He found similar patterns in the German army: declining quality of equipment in 1918, increased use of ersatz materials, falling maintenance standards. The entire German military machine had been degraded by the blockade, but the High Seas Fleet, with its especially demanding requirements for high-quality materials and precision maintenance, showed the effects most dramatically. In 1979, McIntyre published a popular history book, The Fleet That Died in Port: How Industrial Failure Defeated German Naval Power. It became a bestseller, bringing the technical findings to general audiences and reshaping public understanding of naval warfare. The book's conclusion resonated with readers. We remember Jutland as the great naval battle of World War I, and it was. But the actual strategic victory was won silently, gradually, invisibly, in German dockyards where repair crews struggled with inadequate materials, in engineering spaces where machinery degraded from improvised maintenance, in supply offices where requisitions went unfilled because blockade had strangled the industrial infrastructure. The German fleet was defeated not in one dramatic afternoon, but across hundreds of days of material attrition. It is a less romantic story than battleship duels, but it is the truth of how modern industrial war actually works. The salvaged components of Derflinger were eventually placed in maritime museums, in Portsmouth, in Wilhelmshaven, in the Smithsonian. Each artifact carried its lesson, that apparent strength can mask invisible weakness, that industrial capacity determines military capability, that logistics is strategy. The Smithsonian Institution, Washington, D.C., 1980. Exhibition opening. The traveling exhibition, The Iron Truth Technology and Defeat in the German High Seas Fleet, opened at the Smithsonian's National Museum of American History, with a gala attended by naval officers, historians, and policymakers. Dr. McIntyre, now 62 years old and recognized as the world's leading expert on World War I naval materiel, gave the keynote address. He stood before a reconstructed section of Derflinger's engine room, the massive turbines and corroded piping forming a dramatic backdrop. Behind him, screens displayed the evidence his team had gathered: metallurgical analyses, archival photographs, intercepted communications, engineering logs. "Ladies and gentlemen," he began, "what you see behind me is not just a piece of a sunken warship. It is physical evidence of how wars are truly decided in the industrial age. The German High Seas Fleet was not defeated by superior British tactics or by cowardly German admirals. It was defeated by the mathematics of resource accessibility." He detailed the findings: the substandard bearings, the contaminated boilers, the degraded electrical systems, the improvised repairs. Each detail supported the central thesis, that technological sophistication without sustainable logistics is ultimately hollow. The British blockade of Germany, McIntyre explained, was not primarily about starving civilians, though it did that. It was about strangling an industrial system that required global resources to function. Britain had access to those resources through its empire and its naval supremacy. Germany did not. The result was inevitable: gradual degradation of German military capability across all domains, but most measurably in the Navy, where high-technology systems showed the effects most dramatically. He paused before his conclusion, looking at the audience of officers and officials. "The lesson for today is clear. We can build the most sophisticated weapon systems imaginable, but they are only as effective as our ability to maintain them under stress. Supply chain resilience, material redundancy, industrial surge capacity. These are not merely logistical concerns. They are strategic imperatives that determine whether our military capabilities are real or illusory. The German fleet looked formidable in 1919 when it steamed into Scapa Flow, but it was already dead, killed by invisible processes of industrial attrition. We must ensure that we never mistake appearance for reality, that we never confuse impressive technology with sustainable capability. That is the lesson written in the corroded steel of Derfflinger, and it remains as relevant today as it was 60 years ago. The applause was sustained, thoughtful, carrying recognition that the arcane details of marine archaeology had revealed truths about power, capability, and the nature of modern warfare. Decades later, the legacy of the salvage continues. Dr. James McIntyre passed away in 1998 at age 70, but his work on Derfflinger and the High Seas Fleet continued to influence military thinking, historical scholarship, and strategic planning. The salvaged artifacts remained in museums, silent testimony to the lessons he had revealed. In military academies around the world, the case of the German High Seas Fleet became standard curriculum in courses on military logistics and industrial strategy. The question, "What is the use of a fleet in being that cannot actually function as a fleet?" became shorthand for discussions about the relationship between theoretical capability and practical sustainability. Naval planners in the 21st century, dealing with increasingly complex and expensive ships, returned repeatedly to McIntyre's findings. The lesson was stark. A $10 billion aircraft carrier that cannot be maintained is worth less than a $1 billion destroyer that can be kept operational. Investment in logistics infrastructure and supply chain resilience became recognized as equally important to investment in cutting-edge weapons technology. Historians appreciated McIntyre's contribution to methodology. He had demonstrated that material evidence, the physical artifacts of history, could reveal truths that documents alone might obscure, or that contemporary observers might not recognize. The corroded bearings and improvised welds of Derfflinger told a story that German and British reports had missed or concealed. The wreck of Derfflinger still rests in Scapa Flow, now a protected war grave and dive site. What remains of it continues to deteriorate slowly in the cold North Atlantic waters, the steel gradually returning to the iron oxide from which it came. But the lessons extracted from its salvage remain vital. In 2019, on the centenary of the scuttling, a commemorative ceremony was held at Scapa Flow. Among the speakers was Admiral Sir Philip Jones, First Sea Lord of the Royal Navy, who said, "We remember the ships that sank here as symbols of maritime power, but thanks to Dr. McIntyre's work, we also remember them as warnings. They remind us that capability is not just what you can build, but what you can sustain. That industrial strength is as important as tactical skill. That access to resources determines outcomes as much as the courage of crews or the brilliance of commanders. The German sailors who scuttled their ships here believed they were denying their enemies a prize. They didn't realize they were also preserving evidence that would teach future generations how their defeat had actually occurred, not dramatically in battle, but invisibly in workshops and supply depots, in the slow collapse of industrial systems strangled by blockade. War transforms steel into lessons. Salvage reveals hidden truths, and the evidence of material failure can teach strategic wisdom. If this story made you reflect on the relationship between industrial capacity and military power, on the invisible vulnerabilities that underlie apparent strength, share it. Because what we understand about the foundations of sustainable power, we never forget.